Before construction could begin, engineers had to map one of China's most unforgiving mountain crossings. Across this enormous void, the two mountainsides were visible, but connecting them would demand an extraordinary structure. Even reaching the future foundations meant building work platforms on steep rock high above the canyon floor. Then workers would have to raise immense concrete towers while exposed to altitude, wind, and almost no margin for error. So how did engineers build this bridge, step by step, across a canyon that seemed almost impossible to cross? The project represented about 1.028 billion yuan in investment. Yet the first obstacle was simply reaching the canyon. Freight trucks faced steep grades and tight mountain hairpins, making every heavy delivery slow and difficult. The terrain map revealed the problem. Two sides close in space, but separated by a long road journey. Communities could face each other across the gorge, while traveling between them still required hours through the mountains. Small temporary camps brought workers, power, equipment, and basic infrastructure onto both sides of the canyon. With the crossing corridor fixed, engineers could begin measuring the ground that would carry the bridge. A survey control network tied both banks to one coordinate system, so every later measurement would agree. Total stations fixed the tower positions and approach alignments before permanent construction could begin. Core drilling revealed the rock beneath each tower site, where surface appearance alone could never be trusted. Geologists logged each core section, studying fractures, rock quality, and changes hidden beneath the mountain surface. Those cores were matched with geological profiles to identify competent rock and localized fractured or karst zones. Wind stations recorded canyon conditions because high-altitude lifting and cable work depended on safe weather windows. Survey, geology, and wind data finally converged into one buildable plan for the crossing. The final design became a 4-lane steel-truss cable-stayed bridge, 1,341.4 meters long, with a 720-meter main span. Because the two mountainsides differed in elevation, the Guizhou and Yunnan towers required different heights. Every plan locked the same geometry: Guizhou on one side, Yunnan on the other, and the canyon between them. Engineers selected two different main span erection methods, adapting construction to the terrain and logistics on each bank. Before construction accelerated, engineers locked the sequence: foundations, towers, side spans, two erection methods, final closure, then load testing. With the sequence decided, roads, utilities, staging areas, and temporary facilities could finally expand into full construction sites. Before foundations could rise, crews first had to carve reliable access roads into the steep mountain slopes. Heavy-haul convoys crawled through tight bends, bringing drilling equipment and construction materials toward the tower sites. Temporary power, water, ventilation, and drainage transformed narrow terraces into functioning construction platforms. Excavation stripped away weathered material until crews reached stronger rock beneath the future tower foundations. Deep shafts were excavated into the mountain, with ventilation, dewatering, and hoisting operating continuously. Where fractured or karstic rock appeared, crews stabilized the ground with grout before foundation work continued. Long reinforcement cages were lowered into the shafts under controlled rigging, then carefully centered before concreting. Once completed, these deep foundations transferred the enormous future tower loads into competent rock. Dense reinforcement, cooling pipes, and starter bars prepared the massive pile caps for the towers above. After curing and final survey checks, the foundations were ready for the first concrete lifts of the towers. The tower legs began as low concrete lifts rising directly from starter bars, anchored into the pile caps. Climbing formwork advanced upward through repeated cycles of reinforcement, inspection, concrete placement, and curing. At the correct elevation, crews built the dense reinforcement and formwork for the lower crossbeam. Concrete transformed that reinforcement into a rigid crossbeam, tying the two tower legs together. Above the lower crossbeam, both legs continued rising, lift by lift, toward the cable anchorage zones. Embedded steel anchorages and dense reinforcement prepared the upper tower to receive the future stay cables. Inside the tower, guide pipes and access platforms provided the paths and working areas needed for cable anchorage. The upper crossbeam completed the tower frame while the final anchorage zones were finished inside the legs. On the Yunnan side, the second tower reached its final height, slightly lower than the Guizhou Tower. Both towers now stood above the gorge, but the enormous main span between them was still completely empty. Steel for the side spans was assembled on mountainside jigs before main span cantilever erection could begin. Cross girders, bracing, and deck components turned individual truss members into a full-width bridge structure. Once assembled, the side span was aligned on its launching bed and connected to hydraulic pushing equipment. Small test movements verified the hydraulic jacks, sliding shoes, lateral guides, and reaction frames before launching. The complete truss then moved forward slowly, sliding toward the tower under carefully controlled hydraulic force. Push, lock, survey, reset. The cycle repeated until the side span approached its permanent position. On the Yunnan side, another launching system advanced its side span toward the opposite tower. Both side spans were finally in place, yet the 720-meter main crossing remained open between the towers. Now, two different erection systems were prepared to build the two halves of the main span. On the Guizhou side, a full slewing deck crane was anchored directly to strong, completed truss nodes. Individual vertical members were positioned one by one, extending each new truss panel beyond the completed structure. Diagonal members followed, temporarily pinned before survey checks confirmed the new panel geometry. Transverse cross girders connected the two truss planes, creating the width and stiffness required for the roadway. Steel deck components were lowered onto the new bay and aligned with the transverse structure below. High-strength bolts locked the panel together, while surveyors checked elevation, alignment, and twist at the cantilever tip. Only after the steel pass geometry checks were matched, stay cables tensioned in carefully balanced stages, panel by panel and cable by cable. The Guizhou cantilever advanced farther over the canyon. Yunnan used a different strategy. Complete steel truss segments were assembled on the ground before leaving the yard. Every segment was checked for geometry, connections, lifting points, and deck alignment before transport. A synchronized 4-point lifting system raised the completed segment evenly from its support cradles. The weight was then transferred onto 4 transport trolleys suspended beneath the completed bridge truss. Motorized trolleys carried the suspended segment beneath the bridge toward the active erection front. At the cantilever tip, the segment stopped beneath the structure, ready for a second load transfer. A triangular erection crane took the segment's weight, while the transport trolleys were gradually unloaded. The crane raised the segment toward connection level, keeping all 4 corners controlled above the canyon. Hydraulic guides adjusted the segment in 3 directions until cord, web, and deck interfaces aligned. With bolts secured and new cables tensioned, the system moved forward to repeat the entire cycle. As the cantilevers grew, global survey networks tracked both tips from multiple control stations across the canyon. Engineers checked cable forces, steel temperature, deck twist, and tower movement before every critical adjustment. Guizhou completed its final approach panel, leaving precisely prepared steel nodes facing the center gap. Yunnan finished its final full segment, bringing the opposite cantilever into the same near-closure zone. Now only a narrow gap remained between structures built independently from 2 different mountains. At dawn, when temperature was stable and wind was low, surveyors measured that gap one final time. Closure could begin only after temperature, wind, cable forces, and final geometry all entered the required window. The short closure assembly was lifted into the center gap, still separated from both cantilever ends. Hydraulic guides shifted it millimeter by millimeter until the steel interfaces aligned in 3 dimensions. When the final high-strength connections took load, 2 independent cantilevers became one continuous main span. With the main span closed, crews dismantled temporary erection systems and began clearing the structure for finishing work. Waterproofing and asphalt transformed the steel deck into the final 4-lane expressway surface. Permanent barriers, drainage, expansion joints, and lane markings completed the roadway high above the canyon. Ballasted trucks were positioned across this bridge while instruments measured structural response under controlled static loads. Dynamic testing followed, while engineers inspected joints, sensors, and structural behavior before the bridge could open. Then, for the first time, civilian vehicles entered the completed bridge and crossed the canyon in both directions. Freight and passenger traffic could now travel directly between Guizhou and Yunnan instead of circling the mountains. Opened in 2016, Beipanjiang carries a 720-meter main span, roughly 565 meters above the river below.
This video is created for educational and informational purposes using advanced AI tools and human creativity. All concepts scripted and storytelling.